Alright, so this is just a quick video on light. We've already talked about waves, so this kind of just takes some of that information and directs it specifically to waves there, or to light waves rather. So first thing to make sure we address is that light is a type of wave that when it moves through a medium, it pushes that medium perpendicular to the direction that the wave travels. It causes that perpendicular vibration, so that means it's classified as a transverse wave. But light's also capable of traveling through a vacuum, meaning it does not need a medium, and with that classification, it becomes identified as an electromagnetic wave. So light is both a transverse and an electromagnetic wave. So light will travel in a straight line until it reaches some sort of obstacle or barrier, and then what it does with that obstacle barrier depends on what the obstacle or the barrier um, looks like, how big it is. It also depends on the amount of energy in the wave. So different things can happen, but until that, light continues to travel in essentially a straight line. Now, anytime we have energy being transmitted by an electromagnetic wave, we call it radiation, and this includes all types of light. Light we can see, light we don't see. In fact, we kind of can use the word light and electromagnetic wave to be synonymous, to mean the same thing. And generally, the idea of the word radiation kind of gets this negative stigma, like people think that it's a bad thing. Some radiation is dangerous, but not all radiation is. So some things specific about light is that it's incredibly fast, like absolutely incredibly fast. Light can travel at approximately 300 million meters per second. That's not necessarily a speed that you can kind of wrap your head around. You're not overly comfortable with meters per second as a measurement for speed. You know that that's our SI unit, but if we were to look at a unit that's a little more comfortable for us, we'd say that speed travels at about 670 million miles per hour, which is pretty crazy. I mean, just incredibly fast. In fact, we think of sound as being something that's pretty fast, but the speed of sound is only about 340 meters per second through the air, as opposed to almost 3 million meters per second through a vacuum for light. So the speed difference between them is just absolutely incredible. Now, when when light hits a surface and bounces off that surface, just like with all waves, this law of reflection applies. So the law of reflection just says that the angle of incidence is equal to the angle of reflection. So really, kind of simplistically, if I have a reflective surface like a mirror or something, or like, some still water in a pond, when light comes in, it bounces off, and the angle at which it bounces off is going to be very specific. So if you can imagine having this kind of imaginary perpendicular line to your reflective surface, we call it the normal. The angle between the normal and the beam of light that goes in is equal to the angle between the normal and the beam of light that comes off of the reflective surface. So that's all this really says. The angle of incidence is the angle between the normal and the beam of light going in. The angle of reflection is the angle between the normal and the angle of the beam of light that bounces off. So that's all the law of reflection says, and it applies to all waves, not just light waves. But this is what allows me, if I'm standing over here, the light that comes from this side bounces off my mirror and comes over to me over here. So it also allows me to see like across the room by looking into a mirror and things like that. So some other things that happen with light is when light hits matter, sometimes that matter takes in the energy from that light wave, and this is called absorption when that happens. It's like when you're standing outside on a bright sunny day, you can feel the warmth of the sun, you absorb some of the energy, and it makes you hotter. You start taking that energy, you convert it to thermal energy. But sometimes when that energy is absorbed, it's almost immediately re-released. And when this happens, we call it scattering. So like light would pass down through our atmosphere. This is actually what causes our sky to appear to be blue. Light passes down through the atmosphere. Some of that energy gets absorbed by the atmosphere and then re-released. But instead of only continuing to travel in a straight line, when it gets re-released, it kind of travels in all sorts of different directions. And blue light scatters a whole lot, much more than most of the other colors, and that's why the sky ends up appearing blue. So another thing that can happen with waves is refraction, and when this happens with light, what happens is that white light, which is really a combination, we get white light from the sun, white light from most of our light bulbs and things like that. It's really a combination of all the different colors of light combined. So every color is its own unique wavelength and frequency. And when these different wavelengths refract through a material, they bend different amounts because of their different wavelengths. And so if this, depending on the shape of the refraction material, like a prism or like water droplets in the sky sometimes, when white light passes through it, the materials will refract into the light will refract into their own independent band of colors, and it's always in the order from the lowest wavelength and frequency, the highest wavelength and the lowest frequency, red, to the shortest wavelength and the highest frequency, violet. So it always ends up looking at red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. Diffraction is the next interaction that we've learned about so far. And with light, it's just worth mentioning that light, because it has comparatively short wavelengths compared to most other waves, it does not diffract very much. So that's what causes this like cone shape, is the bending of the light around the barrier.
Mr. Martin, please call the main office. Paul Martin, please call the main office.
So light just does not diffract a whole lot. Otherwise, if there was longer wavelengths, so instead of it just being this V shape, you might get light all the way up to the sides. But obviously, that's not the case. Light, short wavelengths, so it's just not going to diffract very much. Interference occurs when waves overlap, and in the case of light, this normally happens due to diffraction, that cone shape. So if you were to look at like the face of a flashlight, like this flashlight here, what you would see is that there's 3 independent LEDs that all produce light. And the light from this one veers out or diffracts, and the light from this bulb diffracts, and the light from this LED diffracts. So,
Mr. Martin, please call the main office. B. Martin, please call the main office.
So where all these beams of light overlap from the diffraction, that's going to be the brightest spot. You're going to have constructive interference happen in those locations. Now, light also sometimes just passes through materials, and when this happens, we call it transmission or transmittance. Some materials allow light to pass through pretty easily, like the air and like the glass in the windows. Other materials not so much, like the curtains and the walls. So materials that allow light to pass through really, really easily are referred to as being transparent. Light passes directly through them. It maybe has some refraction, but that's pretty much it. Other materials allow light to pass through, but you get this kind of foggy sort of look. This is what we refer to as being translucent. So light passes through, but some of the light scatters as it passes through, so you don't get a real clear image of what's on the other side. But then other materials are considered opaque, and opaque just means that light doesn't really pass through them at all. So when we talk about light passing through things, or just light in general, it's important that we understand that when light is coming to us from a light source, white light is the result of all the different colors of light reaching your eye together. So if light from a lamp overhead hits a white piece of paper, all the different wavelengths bounce off of that piece of paper and reach your eye. And that's what you see as being white. When you see something as being black, on the other hand, it means that all the colors of light hit that object, or only maybe some colors of light hit that object. But light waves do not reflect off of that object to reach your eye. So when you see the color black, what you're really seeing is the absence of color. When you see a specific color, like say you have a piece of green paper, what that means is that light has struck that paper, and green light waves have reflected off and come back to your eye, but the other colors of light have all been absorbed. So the only color that you would see is the colors that are reflected. And because of that, that's kind of plays a role in why we wear dark clothes in winter but light clothes in summer. Light clothes are going to reflect away a lot more of that light, so it doesn't get absorbed and turned into heat, where dark clothes absorb a lot more energy and can convert that into heat. So in winter, when you're trying to stay warm, you would want to capture as much of that energy and turn it into heat as possible. But in the summer, when you're trying to stay cool, you want to reflect that energy away rather than have that be absorbed in your clothes. The electromagnetic spectrum is this band of all the electromagnetic waves. So it's just kind of a visual representation. And what you'll see is that it starts on one side with long wavelengths and low frequencies, and we call these radio waves. And then we have like kind of we have 7 different sets of waves, with ending with gamma waves over here, which have very high frequencies and very short wavelengths. This means that gamma waves have a lot of energy. These are the types of radiation that can be really getting into pretty dangerous stuff. But these waves down here are pretty low energy. They're really not something that we have to be all that concerned about in terms of being dangerous. And kind of splitting the sets of waves right in the middle is our visible light. This is the light that we can see. So radio waves have really long wavelengths and low frequencies, and that makes them very low energy waves. These are the types of waves that are used for radio broadcasts, so like your AM and FM radio. If you've ever watched TV from an antenna, that's the way those are broadcast as well. These are also used a lot with cell phones and things like that, to broadcast. Your cell phone signals are using radio waves. Microwaves, on the other hand, have a little bit more energy. They're not a ton of energy, but they're a little bit more. Your microwave oven actually uses these waves because these waves are really easily absorbed by water and turned into heat. So when you cook your food, your microwave oven emits microwaves that are absorbed by the water. The water gets hot, and then the hot water is what cooks your food. They're also used in radar, where waves will be sent out from a tower, and they bounce off an object and come back to the radio tower. And how long it takes for those waves to come back tells us about how far away an object is. And if the amount of time it takes for these waves to come back is decreasing, then that means that the object's moving toward us. Or if it's increasing, it means the object's moving away. How many of these waves get bounced back to us tells us about the size and shape of the object. So it's kind of another location where microwaves are being used. We also have infrared waves. Infrared waves are waves we get a lot of from the sun. These 3 sets of waves we get a lot of from the sun. Infrared waves, that prefix infra means below, so these are waves with a frequency below that of the color red. We cannot see them, but we do feel them. We feel them as heat. So this is where you might have infrared lamps or heat lamps that are used in the cooking industry. When they put food out and they put lamps above them, these lamps emit a lot of infrared waves, and that keeps your food warm. So we get a lot of this energy from the sun. Next, we run into our visible light spectrum, and this is just kind of our middle set of waves. These are the ones that we have sensory receptors in our eyes that can pick up these waves, and they're arranged by color. So each frequency and wavelength has its own, appears to be its own color. So red, orange, yellow, green, blue, indigo, and then violet are arrangements of colors from the lowest energy with the longest wavelength and highest frequency in red to violet, which has the highest frequency, the shortest wavelength, and the most energy. So red, longest wavelength, lowest frequency, lowest energy. Violet is the shortest wavelength, highest frequency, highest energy. And that's the way the rainbow is always arranged, is based on that specific set of colors in that order. Now, ultraviolet waves are another type of wave we get a lot of from the sun. That prefix ultra means above, so these are waves with frequencies above that of the color violet. And these are the types of waves that could potentially cause skin cancer and sunburn if you get too much of them. But there's also some real benefits to these. You need to get some ultraviolet waves on your skin because they react with your skin to create vitamin D, which is necessary to maintain health. They also can be used to sterilize and kill bacteria and viruses. So sometimes they're used in the medical industry that way, to sterilize equipment without having to use chemicals. Oh, sorry, I jumped back to the wrong screen there. Our next wave here is our X-rays. X-rays have even more energy still. Now we're really starting to get in the waves that can be potentially hazardous. These waves have so much energy that they pass directly through your soft tissues like your skin, your muscle, your tendons and ligaments, but not your bones. They'll reflect off of your bones. So this allows doctors to take a picture of your skeleton to see if there's any injuries to the bone itself if you get injured. That way, if you go to the doctor with a leg injury, they don't need to cut your leg open to see if there's a break. They can just take a picture and treat it appropriately. So these are pretty dangerous, though. So it's someone that works as a radiologist, someone who takes X-rays, would not be in the room with you typically where you're getting x-rays, because they can't be exposed to them over and over and over again every day. And if you ever have to go get an x-ray done, you'll see that they give you these big heavy aprons that are really often they have metal inside of them, and that prevents x-rays from getting into your body somewhere they're not supposed to be if you have to have an x-ray taken. So that if you have to have an x-ray taken of your arm, only your arm is being exposed to those x-rays, not your internal organs like your heart and lungs and liver and kidneys and that sort of stuff. And then lastly, we talk about gamma rays. Gamma rays are the electromagnetic waves with the most energy. These have really high frequencies and very, very short wavelengths. And these can burn through organic tissue like your skin. Now, this can be useful to us when we have cells that are not what they're supposed to be, cancer cells. They've mutated and are reproducing. So gamma waves, in the form of what they call a gamma knife, can be used to kill those cancer cells, to destroy those cells so that they can't reproduce and create more cancer cells. But obviously any healthy tissue that's exposed to these will also be damaged. So this is not always the right tool for treatment of cancer, but sometimes it is. So that's our basic set of information on electromagnetic waves and the electromagnetic spectrum and light waves. But if you have any questions, please make sure you shoot me an email. Thank you.